All right, we're now in section 8.8. This is called improper integrals. Improper integrals occur when you are taking the integral and it goes to infinity. So they've given us three rules, one to cover each of the cases. If we are going from a to infinity of some function, f of x dx, that would be the same as taking the limit as b approaches infinity and change the infinity to a b. So you'd work the problem just like you normally would, plugging in your a and your b, and then you would let b go to infinity. A would be a number and b would just be a b. Likewise, if it goes from negative infinity to b, then you're going to change out the limit and make a go to negative infinity and write it as a to b f of x dx. So we are combining an integral and a limit. Now the third one is a combination of the first two. If the problem goes from negative infinity to infinity, then we need to split it into two pieces. We need to have the limit as a goes to negative infinity, and we're going to split it somewhere between negative infinity, and we're going to call it c. So we're going to go from a to c. So that's negative infinity to some number c. Then we're going to add to it the rest of the problem, the limit as b goes to infinity, pick up at c, and go to b. So those are your three major rules. So let's look at example 1. They want us to integrate from 0 to infinity e to the negative 3x dx. So we rewrite it, and it doesn't really matter what letter you use here. I'll just use a b because they've been using a b. 0 to b of e to the negative 3x dx. Okay, we can do that. That's going to be the limit as b goes to infinity. The integral of e to the negative 3x is negative 1/3 e to the negative 3x from 0 to b. Now we do our plug and chug. So we have our negative 1/3, and the book turned it around, but I'm not going to. Negative 1/3 e to the negative 3b minus e to the 0. E to the 0, that turns into 1. So now I'm taking the limit, and this is really, well, let me write it one more time. That's still infinity. This is negative 1/3, and then it's 1 over e to the 3b. As b goes to infinity, the denominator becomes larger and larger, and 1 divided by a very large number from before is a very small number, so 0, and so I get negative 1/3 times negative 1, which is 1/3. And that was part A. Part B. Integrate from negative infinity to infinity, so we're going to split this into two, dx over 1 plus x squared. Hopefully you're recognizing that 1 over 1 plus x squared as an arctan, but we need to write it as the limit as a goes to negative infinity. Pick a number c. Now, I'm going to pick a convenient number. I'm going to call it 0. 0 is a nice, easy number to work with. Of 1 over 1 plus x squared dx, plus, then we're going to have the limit as b goes to infinity. We're going to start at 0 and go to b. And then when we integrate, this turns into an arctan of x from a to 0. This one's going to positive infinity. Same exact problem, only it's from 0 to b. So now we have arctan of 0 minus arctan of a. And this one's going to be arctan of b minus arctan of 0. Okay, when is the tangent 0? It is 0 at 0. When is the tangent, we're looking at this guy right here now, when is the tangent going to be a negative infinity? If you think about what the tangent curve looks like, you have asymptotes here and here. This is at negative pi over 2. This is at pi over 2. So when is it approaching negative infinity? It's approaching negative infinity at negative pi over 2. So this is going to be 0 minus a negative pi over 2 plus, where does it approach positive infinity? When it gets to pi over 2. And so I end up with pi for an answer. So let's look now at example 2. It says, consider the family of functions 1 over x to the p, where p is a real number. For what values of p will this function, the integral from 1 to infinity of f of x dx, converge? All right, so we are trying to integrate that problem, which we're going to turn into a limit as b goes to infinity, 1 to b, 1 over x to the p dx. Now, if I just integrate this, I would, well, let me rewrite it. This means 1 to b of x to the negative p dx. I would raise the power and flip it in front. So if I raise the power, it's going to be 1 minus p, or p, negative p plus 1, and I have to flip it over. I'm just going to write it as 1 minus p instead of negative p plus 1. And then I have x to the 1 minus p from 1 to b. Now that 1 over 1 minus p can come on the outside because there's no b's in it. And if I plug and chug, I'm going to have x to the, oh not x, sorry, b to the 1 minus p subtract 1 to the 1 minus p. Now we get three cases here that we have to look at. Case 1 is if p is greater than 0. If we are looking at p greater than 0 and we're trying to evaluate this limit, now let me take one more step before I do that. This is just going to be 1 over 1 minus p, the limit as b goes to infinity of b to the 1 minus p, subtract 1. So if p is greater than 0, what's going to happen to the problem? Well, this little guy right here would be approaching 0. So all I would have left is whatever 1 over p minus 1 is. Case 2, if p is less than 0, that would mean that p, 1 minus p, why did I write it backwards? Hang on. Oh, wait. I jumped it on you, and you're not going to understand what happened. If p is greater than 0, then that means that p minus 1 will be greater than 0. Agree? If p is greater than 0 and I subtract 1, then p minus 1. That'll work. As long as p is greater than 1. So that's going to work. And if that's the case, then I'm just going to end up with the negative 1, which is over here, this guy here, times the 1 over 1 minus p, and that gives you 1 over p minus 1. So that's how I got there. If p is less than 0, greater than 1, not less than 0. Let me fix all these. I'm making a big mistake here. Ones. We got to break it at 1 because that's where the issue's happening. If p is less than 1, then I could say that 1 minus p would be greater than 0. And if that's the case, then this little guy at the end here, and I can't keep writing in the same place, the b to the 1 minus p would get extremely large. This guy right here would get very, very large. Arbitrarily large is going to go to infinity, so the answer would be infinity. So I have this answer in case 1, I have this answer in case 2. Case 3 would be what happens when p equals 1. If p equals 1, then I'm integrating. What's going to happen here? If p is 1, I end up with, if p is 1, that 1 over 1 minus p part of it, let me rewrite what I've got here. This piece is going to end up getting larger and larger and larger. As p gets closer to 1, the denominator is getting tinier and tinier, and 1 divided by a teeny tiny number is a great big number. And then the rest of it's just going to wipe out, because if you put a 1 in there, you're going to get b to the 0, which is 1. Yeah, it's close to 1. And I subtract it, infinity is going to win out. So it's going to go. So here's the problem. The question said, when does it converge? So the bottom line is converge or diverge. Bottom line is, if p is greater than 1, we converge, because we can actually get an answer. So p greater than 1 converges, but if p is less than or equal to 1, it's going to diverge. And the reason they're using a p here, this will eventually be called a p series. And so you'll be able to look at any problem I give you, and if you know what the exponent is, if it's greater than 1, it converges. If it's less than or equal to 1, it diverges.